And our second session is called Tracking and Improving Building Performance, where we will hear from speakers about some of the planning aspects we learned about a little bit ago and how those are put into practice and then continued on a couple different campuses. So I will be moderating our session for today, but then we will hear from Dooley West from the University of British Columbia, John Elliott from Sustainable Berkeley Lab, and then John Deffenbaugh from Pennsylvania State University. And just like the last session, we're going to have 3 speakers, about 20 minutes each, and then we'll have time for Q&A after. So please put your questions in the chat and we'll get to as many as we can. I've been really impressed with the engagement of the audience, so I'd love to see that continued. So our first speaker for today is Dooley West, who is a Senior Energy Conservation Manager at the University of British Columbia and has 14 years of experience in energy conservation, new construction, and sustainable building experience. Dooley has worked at UBC in her role in energy and carbon reduction of existing and new buildings on campus for the last 7 years to help the university reach its energy and carbon reduction goals. And before her time at UBC, Dooley worked as a mechanical engineer in new and existing building consulting in both Vancouver and Toronto. So please welcome Dooley West.
Thanks, Brianna. Can everybody hear me okay?
Yes.
Great. Thanks everybody for joining me here today. I'm with the University of British Columbia, and thank you for the introduction. I'm here to speak to you about achieving a 40% reduction in energy use from our largest lab building on campus, and talk to you a little bit about, give you a bit of an overview of the campus and how we've structured our energy group here to achieve substantial savings and energy reduction for the university. So a little bit about the UBC campus. We're located in Vancouver, British Columbia. We're a single owner occupied campus of around 1,000 acres, and we have a daytime population of roughly 70,000 people, 18 million square feet of floor space, an annual average growth rate of roughly 200,000 square feet a year. And I work for the utilities department for the university. We have roughly a $54 million commodities budget where we pay for the utility costs, and we own the heating infrastructure, the district energy system, electrical infrastructure, water systems, and sewer systems. A little bit about my group. I work within the utilities department in a group called Energy Conservation and Innovation. We were initiated in 2014. We have roughly 5 BMS techs, a BMS manager, 4 energy conservation engineers, a data analyst, and myself, the energy conservation manager. We implement roughly 200 to 500K in BMS projects a year. And roughly $1 million in energy conservation projects a year. This funding comes from a revolving fund that was set up through our utilities department because we pay for the utilities for campus every time we do an energy conservation project. It has a positive net benefit to our budget, basically. And we get roughly anywhere from 300 to 500K in incentives every year to put towards this $1 million budget. And we also focus on a lot of controls changes in the buildings, not just capital projects, which is why the BMS group is within our department as well, as we work very closely with them to be able to implement these projects properly. We have internal demand side management targets of roughly 20,000 gigajoules a year and 4 gigawatt hours of electricity. And these targets were originally set to offset that 200,000 square foot campus growth that we see every year, to basically prevent our commodities budget from growing too much. And when we look at the energy story of our campus, we have been able to hold fairly consistent the amount of energy that the campus consumes despite growing floor area. So this graph we have on the y-axis, the campus energy in gigawatt hours. and on the x-axis, the fiscal year. And in the early 2000s, we undertook a major eco-trek project where we looked at all of our campus buildings and started doing energy conservation in them through a consultant. And then in 2014, our department was formed, and since then you can see energy consumption on campus start to decline. And in that gap year, you can see it started to go up. And the orange line here is campus floor area. So you can see that as our campus has grown, we've been able to keep our energy fairly consistent without huge growth at the same level. In terms of our cumulative savings since the early 2000s, we do track this, although it hasn't been updated in a few years. And our cumulative savings in fiscal year 20 was roughly $90 million from the early 2000s. So you can see that setting up your department and investing in energy conservation projects for the university does have a fairly significant net benefit in terms of a positive business case for these projects. Before getting into life sciences, I also wanted to touch a little bit, because of the theme of the conference is on decarbonization. I wanted to talk about our district energy system on campus. We have 3 15 megawatt natural gas boilers, a bioenergy plant of 6 megawatts that's currently in commissioning to be expanded to 12, and a 2.4 megawatt cogen engine. And we converted from a steam to hot water system in 2015, and that, along with demand side management, helped us get to a 30% reduction target in, I think it's 2017, below 2007 levels for our GHG emissions. And we're looking forward to a 60% reduction in GHG emissions by 2023, once the biomass expansion is complete and commissioned. We have new decarbonization targets. Originally, our target was net zero by 2050, and it's now been moved up to 85% reduction below 2007 by 2030. 100% of the energy used by DES needs to come from low carbon sources by 2030, and a net zero campus target by 2035. So that gives you kind of the big picture here of the campus. And I'd like to dive into a little bit, not a little bit, actually a lot, on our largest building on campus, and showing all of you how we do energy conservation on campus and the types of things that we implement. So Life Sciences Center is our largest building on campus, and we have achieved roughly a 45% reduction in building energy use in this building. It's the largest teaching and research building of roughly 560,000 square feet. It is a medical research and education facility with animal care and level 3 biohazard lab. It represents roughly 4% of campus space and 10% of campus energy use. When it was originally built, it used an exorbitant amount of energy, roughly 2.5 times more than was originally modeled by doing the LEED certification of it. And this graph gives you an idea of the energy use intensity. So on the y-axis, we have kilowatt hours per square meter of energy consumption for the building. And then you can see throughout the fiscal years how we've been able to reduce that by roughly $840,000 a year. The building has 34 air handling units, 10 exhaust systems, high plume exhaust fans, strobic fans, roughly 780,000 CFM of makeup air, 12 to 14 air changes, or that's what it started with, 380 ton screw chillers, exhaust air heat recovery, and preheat coils in the large air handling units, and 1,000 kilowatt plate and frame heat exchanger for condenser water heat recovery. In the initial approach for energy conservation on campus, we relied heavily on consultants to do energy savings opportunities. Those were as a result of kind of the eco-trek years, and we were really just scratching the surface on what we could do on campus. And so the initial approach took partnering with BC Hydro and doing a campus-wide building tune-up program through their fair incentive system, and we were able to do a lot of simple controls changes in the buildings, not just life sciences, but across campus, things like outdoor air temperature lockout, weather prediction, classes off-road scheduling adjustments, and optimizing domestic hot water systems. We found that these had less than a 1 year payback in this building in particular, and saved roughly 3% alone on its energy consumption, roughly 3,600 gigajoules and 300 megawatt hours of electricity use. I got a lot of info here, so I'm going to move through these pretty quickly. The next thing that we looked at on campus, and particularly in this building, was coil cleaning. There hadn't been a lot of maintenance done on coil cleaning or filter changing in our buildings. And when we had somebody come in and look at them, we found a lot of dirt and debris, mold and bacteria. And so we put together a coil cleaning program as well as a filter changing program. And both of these basically allowed us to reduce energy consumption through reduced static pressure on campus, have better air quality. And we also changed the filters on campus from MERV 8 and MERV 13 to MERV 14 mini plate, which allowed us to reduce maintenance on campus as well. And that had pretty substantial savings, roughly 1% for the filters and 1% for the coil cleaning in this building. Digging a lot deeper, we had a dedicated energy management team from 2010 onwards. And so we were able to really look at the buildings in much more depth to figure out how can we save energy. And one of the things that was the most obvious at life sciences was that we were rejecting a lot of waste heat from the building. Roughly 1 megawatt of waste heat was rejected from life sciences on a typical winter day, and we could be using that heat within the building. And when we looked at the heating water schematic, I mentioned before that we do have a plate and frame. We do have a heat exchanger that was supposed to be used for heat recovery from the chilled water system condenser side to the heating system in the building. Let's see if I can get the work. That's this heat exchanger here. And the reason we found that it wasn't working, and there are 2 reasons why this wasn't working. One is that there was a manual bypass that was open that was basically allowing flow to be rejected around the hex. And so there wasn't actually any flow going through it. And then the second was temperature. So the temperature of the condenser water loop was less than the heating water return temperature. So it's just not possible to actually inject heat into the heating system. And so what was done is that we decreased the heating water supply set point, which then decreased the return set point to a level that we could increase, that we could actually reject heat into it, and then close the bypass valve slightly so that it forced flow through the heat exchanger. The results were pretty substantial. This shows the baseline case before the change in the dotted line, and then post after the change in the green line. You see fairly substantial savings in steam reduction, roughly 1,800 pounds per hour, or roughly 14,000 gigajoules per year, 9% of the building's energy consumption. And we find this is not abnormal at all. We find this in a lot of our new construction buildings, that there's things that just were supposed to work that don't work at all to begin with. And our energy team here spends a lot of time trying to get the systems actually working the way they were designed to. Next, looking at the chilled water system. The chilled water system we found had 2 chillers operating most of the time with an average COP of 3 and a fairly low supply water temperature, roughly 4 degrees Celsius or 40 Fahrenheit for you people in the imperial system, and return of 49. And what we were able to do was basically reduce or increase that supply water temperature up from 4 to 7, and then it also increased the return, and it increase the COPs on the chiller from 3 to 5. And as a result of that, only one chiller had to run rather than 2. And for those of you that know chillers, they do like to be loaded up in terms of efficiency. And the results were roughly 150 kilowatts of electrical savings because of the magnitude of this building. Small changes in programming or operation have huge savings in energy reduction. And that is one of the things when you're looking at energy conservation, is to really try to focus on the larger systems and the larger buildings, because you get a lot more kind of bang for your buck when you're spending time. You need to think about, what am I going to spend my time on? You're going to spend your time on the larger systems. And then really getting into the excavating for this building, diving deeper into it. You've seen this chart already today on a different presentation, but it's the same thing. It's a chart of the heating and cooling requirements for the building, and what was found at this building and in a lot of buildings is that you do have simultaneous heating and cooling loads, and especially in our lab buildings that have animal care facilities, we have constant cooling requirements. And so even though we had optimized the heat exchanger to recover heat, there was still a large opportunity to recover more waste heat from the cooling system. And so what was done is a dedicated heat recovery chiller was installed to provide to basically use that waste heat from the condenser side, bump it up in temperature, and recover it into the building heating side. And that saved roughly 10,000 gigajoules per year, or 7% of the building's energy consumption. Another project that we worked on, and we've worked on this one on a number of buildings, not just life sciences, is the optimization of 28 high plume exhaust fans. These are strobic fans that run basically 24/7 to provide or exhaust the air that's needed in our laboratory buildings. And what we did is we hired a consultant to do wind tunnel testing of this building and review the worst case scenario for plume height requirements. And basically what we were able to do is adjust the maximum plume height that the strobic fans were exhausting air to, while at the same time also closing bypass dampers. And so when you look at, this is a BMS graphic of a exhaust fan system, and how it works is that you've got air coming in, exhaust air from the laboratory that's being exhausted out of these exhaust air, and then you also have outdoor air coming in that mixes and essentially gets exhausted out. And so what we are able to do is basically close these bypass dampers, and then that in turn reduces the speed of the variable speed drive, which has substantial savings. At the same time, running, originally we would have 2 of these exhaust fans. They're duty standby. There's one fan that's always there for redundancy, and at the beginning only 2 of the 3 fans would run, and it's actually more efficient to have all 3 fans run at the same time on the fan curve than have at a lower speed than have 2 of the fans run at a higher speed. And so this is a project that we implemented at Life Science Center, but on a number of systems on campus, and had a 6-year payback for this project in particular, and roughly a 60% reduction in fan energy, saving roughly 5% of the building's energy use. At the same time, this building was an older building built in, I think, 2004, and it had fairly high air changes in the laboratories, roughly 12 to 14 air changes during the day, and 6 in unoccupied mode. And what UBC implemented a new standard to have 8 and 4 occupied versus unoccupied. And we were able to adjust the air changes down from 12 and 6 to 8 and 4, reducing the amount of outdoor air in this building by roughly 100,000 CFM. This had a substantial impact on the energy use of the building roughly 8% and less than a 1-year payback because it took some engineering and controls changes by the BMS crew. So looking at this building on a whole, the cost savings summary of all of these ECMs, the CapEx for all of them is roughly $1.4 million. We received roughly $500,000 in utility incentives, another $600,000 in grants, and the cost to UBC was only $240,000, and we're looking at $580,000 cost savings per year. That number is actually higher. This chart hasn't been updated. And the payback to UBC is less than 1 year, but you can see with the cost savings, even without, if you get rid of the incentives and the grants and just look at the CapEx, $600,000 in cost savings per year with a CapEx of 1.4 is a less than 3-year payback. And so these projects with controls changes are a good investment for most institutions. And so the key takeaways from my presentation are that having a dedicated energy team to look at buildings is a good idea because it gives you the confidence to be able to implement energy conservation projects, both in controls changes and in capital infrastructure. And then focus first on simple changes to the control system to get it working properly, and also set up a revolving fund so that you are basically taking a portion of those energy savings and then feeding it back into future projects so you can fund it. And I think the questions are going to happen after all of the other presentations. So thank you very much.
Julie, thank you so much. I know that's a lot of detail to fit in not a lot of time, but I think you did a really great job telling the story. And I mean, clearly UBC is a great example of how to put some of these things into play. So please post questions in the chat and we will get to them after our next 2 speakers. But we'll move on to next hear from John Elliott, who is the Chief Sustainability Officer at Lawrence Berkeley National Lab. And he is responsible for directing and implementing the lab's sustainability strategy across climate, energy, waste, and water. He was previously the Director of Energy and Sustainability at UC Merced. So please welcome John Elliott.
Great, thank you very much, Brianna, and great work, Julie, and great presentation. I'm going to talk to you today about the ongoing commissioning program at Berkeley Lab. So this is very much, it's a great segue from Julie's presentation because this is our particular version of deploying a dedicated energy team. We've been doing it for some time, so this is framed as a 5-year update. And I'll also give you a little bit of context in a similar way that Julie did. So Berkeley Lab is a DOE national laboratory that's run by the University of California, and by UC and UBC standards, we're relatively small, about 2 million square feet of built space on our main site, kind of sprawled across the Berkeley Hills, about 5,000 maximum daily population pre-COVID. So we're a research campus dominated by laboratories and scientific equipment. I'll also say too that I am the sponsor of our ongoing commissioning team, but Chris Wyant, who has spoken to you in previous years, is the leader, the actual leader of the team. He's traveling right now, so he wasn't able to present, but I believe he is online, and if his internet at the hotel is working well enough, he should be able to answer some questions as well. So I'll give you just a high-level overview of the process. In previous years, we've gone into more depth. I'll note too that our ongoing commissioning process is inspired and taken quite directly from the Scrum methodology that was developed for software development. So many people are using it, but perhaps it's somewhat novel to apply it to work on buildings. So these are the key elements. So one is assembling a team, a cross-functional dedicated team. So this is kind of pulling some people away from the work ticket process and making sure you have a core group of people that cover the set of skills you need to fix the complicated problems that we see in our buildings. Second piece, and this is really core, is a repeated cycle. So we call this a sprint cycle. This comes from Scrum. We have a monthly sprint. And in that sprint, every month, we're selecting opportunities, or what we also call building deficiencies, from a backlog that's always being maintained. The team is completing the work. We're verifying that the work was done correctly, and we verify any savings we've generated, generally from several different opportunities added up. And then we post those savings up to our website at the end of each sprint. A key part is teamwork. So there's daily team check-ins. These are ideally quite short, about 15 minutes, but it's a way just to keep the team working together. And it's a way to quickly identify any barriers that are coming up and to resolve them. The process also involves regular feedback. So there's this kind of continual improvement idea. So one way we do this is at the end of every sprint, we're having a sprint review and retrospective. So the whole team gets together. We all talk about what was completed. We identify what worked well, what didn't work well, and we identify any process improvements, and then we start the sprint again. The last piece, and this isn't really from the Scrum, but it's important for us, is we're very focused on maintaining any savings that we generate, because this efficiency is kind of the foundation for an overall decarbonization strategy for the lab. So we don't want our efficiency savings to go away. So we're using tools like SkySpark to help us maintain those savings, and a lot of process. And in our case, we use the ISO 50001 energy management standard as a way to move a whole bunch of things across our organization forward. And that helps make sure that our energy management is strategic, effective, and persistent in this case. Let's see, my slide advance just stopped. Great. So I guess I am somewhat proud that we've kept up this discipline for 5 years. On Monday, we just finished our 59th sprint. And the OCX process here is really all about the process. And so you can get, when you get the presentation, you can link here. You can see all of the items we've closed to date. There's over 800 items. We're closing about 100 significant items each year. And then there's always this backlog that's bubbling in the background that we're taking items out of each month, but we're also putting new items that we're identifying mostly through SkySpark review there. And along the way of doing this for 5 years, we've gotten some recognition for these efforts. So there is a real team, there's real people behind this effort, and you can get a little bit more sense. So one thing I'll say is that this is a joint project across my sustainability organization and the facilities maintenance organization. So all the people on the top here are from facilities management, and all of the people on the bottom here are from Sustainable Berkeley Lab. As I mentioned, Chris Wyant is the leader. He's the senior controls engineer. You can also think of him as a Scrum product manager. So he's really guiding the day-to-day activities and is very core to the monthly sprint planning process. We have dedicated technicians. In this case, we sort of always have 2 dedicated technicians, Ricky and Matt here. I think the OCX process has been great for allowing them to focus instead of running from work order to work order. They have more time to really focus and stay with problems. And it's been really, really great to see them grow over the years. They're very smart, and this process is giving them the opportunity to really advance in their careers and start doing things like controls programming and so forth. We have other people in facilities that are sometimes working on the team, but they tend to be organized around work tickets. So these are the other people on that top row. And then we have other important people like Deirdre Carter, our energy manager, Kushal, that are also contributing to the strategic direction and kind of identifying data anomalies and so forth that help us identify ongoing commissioning deficiencies as we continue. I'll say that ongoing commissioning at our lab has really been driving all of our efficiency savings across the site. So we've gotten such a great return from the ongoing commissioning process that we haven't been doing a lot of big capital intensive retrofits. very similar to, I think, the spirit of Julie's presentation. So whether it's work in our general building stock or work in our high performance computing center, the cooling plant there, or even in new construction, we see that the ongoing commissioning team is core to generating and maintaining those savings. As Julie said, when we get a new building, we might have a very good design, but it takes a lot of work to dial it in and maintain those savings. So for us, this growing portfolio that we maintain has grown. It amounts to 13.4 million kilowatt hours a year. So that's in units of kilowatt hours, but it's actually expressing savings across electricity and gas. That's a savings of over 1.2 million in utility costs a year. And as I mentioned, we're quite a bit smaller than the UBC numbers there. But this, just to get a feel, is about twice as much as it costs, in all of the labor costs and material costs that are going into the OCX program. So a continual return of less than a year. Previous chart of an expression of the degree of savings. This is also just looking at the energy consumption per square foot. This is one of the key metrics that we use, where we're just looking at the general building stock across the lab. So I've subtracted out some big process loads, some computing and accelerator process loads that are turned on and off according to schedule. But you can see that our overall energy consumption per square foot in the general building stock is 30% lower than where it was in 2015. And in gas, we're 39% lower there. And that actually corresponds to a 34% absolute reduction. And you can go and you can see these, we update these numbers every 6 months, and you can go to sbl.lbl.gov/data to do that. So that's kind of the high level overview of OCX and why it's important to us. I will lead you to some other sources of information and detail. So we have a couple informal websites, ocx.lbl.gov, that talks more about ongoing commissioning. And in particular, I would direct you to an ACEEE 10-page paper that describes the process in detail. It's from 2020, but it's all still accurate in what we're doing. We also have another website, Data Analytics for Operations, or da4ops.lbl.gov. And you can see a lot of different screenshots, ways that we're using SkySpark in this commissioning process, whether it's just visualizing gas consumption at a whole building level over a very long time period, like in this chart here for 5 years. And we sort of use this to make sure that the savings improvements are still working in our buildings, or as an example, up in the upper right, where we might be looking at the zone. And in this chart, we're looking at what temperatures we expect to see in a zone given the reheat coil position, and it helps us identify reheat coils or valves that are not working properly, and we can go out and fix them. There's many other visualizations at that website. So now I'll just provide a few observations of where we're headed at this 5-year milestone, and I'll put them in 3 categories. So one is we're focusing more and more on getting better at maintaining savings. So I showed you those 2 efficiency charts. You see that our annual generation of savings is reducing a bit over time, but we see a lot of efficiency savings at the meter. So we're trying to get better and better at making sure we can maintain our savings. We also just continue to work in different areas, and so we're exploring different areas and deepening our understanding. And then, of course, you have to keep finding more energy savings. So you sort of have this process, the ongoing commissioning process, but you have to keep remaining creative and go after and continue to find savings. So here's a little bit more detail behind this. I'm going to go through this briefly to give you a sense, and then I'll show you a few slides related to the items in green on this chart. So I've mentioned several times that maintaining savings is very important to us. And we've actually had 2 ways that we've done this historically. So we have a process, it's a regression analysis that's done every 6 months. Raphael Vitti in our group does this, in which we're looking at each building in which we've done work. And with regression analysis, we're comparing the actual performance of that building to expected performance given current weather. So there's kind of a 6-month check that we're doing to make sure that the savings that we generated is still there. We have another process in which we're looking at all of the meter reads that come in every month. So this is across hundreds of electricity and gas meters. And we also do a regression analysis there where we're comparing the monthly consumption to what we expect to see based on a regression from previous year's data. So it allows us to flag any anomalies, and then we go investigate those monthly readings. And often it can be just data quality problems, but it can also identify something that's gone wrong and is consuming a lot of energy, or some sort of new energy use or water use that we weren't aware of, and then we can go investigate it. But more and more, we've been interested in identifying things that are wasting energy immediately within a day or two. And so we've been working on automated consumption alerts for a more rapid response, and I'll show you a bit more about that. We've gotten into 2 areas and I think learned quite a bit, and I think these have some implication for further energy savings. So one is sensor calibration, and the other is deploying and using lighting occupancy control sensors. And I'll talk to you a little bit more about that. And then, of course, as I said, you have to keep finding more energy savings. So one strategy that we're pursuing, I think, has general applicability, which is just doing better scheduling, both at the air handler level and at the zone level. So I'll talk a little bit more about that. And then we have other things that we're doing to get more energy savings. We have 2 significant computing facilities that we'll do more work in. One of them's new in a large computing facility where we've done work for years, but between these 2 facilities, I think there's some more significant savings that we can find. We have several building automation system upgrades that are happening across the site. So as we get those new systems, we expect to have greater visibility to the poor operation in those buildings, and we'll find savings there. And then, of course, we're talking about electrification and decarbonization today. So we do anticipate doing significant retrofit electrification projects. And of course, those with the COP improvement can drastically lower your EUI. And when we go in and do those projects, which are quite deep into the building, we'll also be doing efficiency measures as well. So let's just touch on the last few items. Here are these 4 items, and we'll do that. So I think you're all familiar with alarming in building automation systems. And every time I've been close to those systems, they're always kind of out of control. You have tons of alarms coming. I think it's a kind of ubiquitous problem across many facilities organizations. So we've worked, this is the work of Raphael Vitti in our group, to make a slightly more sophisticated version of alarms. This is happening in our SkySpark system, which is integrated to several building automation systems. And we've just structured it in a way, we've actually structured it in a way to try to limit the number of alarms to those things that are really important to us. So we're building up a set of automated consumption alerts. They get applied to a particular data point. We have actually 3 variables that we're setting. So one is a threshold, just like you in an alarm. Has consumption a certain threshold, but we also define 2 other variables. One is a watch period that we're looking at, and then we set a threshold of the number of occurrences in which the first threshold needs to be exceeded before it will trigger an alarm. So you can see on the right, here's an example where you could have several cases where you actually exceed the threshold, but because it doesn't happen continuously, we don't want it to trigger an alarm, and we only want it to trigger an alarm when you have a case where you've had a certain number of exceedances over a certain period. So this is one little strategy to sort of clean up the alarms, and we're building this up over time. And it's proven very useful to identify a lot of water waste that occurs, but also in other systems as well. And we can respond quite quickly to this. Another area in which we've been doing many different activities is in scheduling. So a lot of this is happening at the air handler level. We're using primarily Wi-Fi data, all of the Wi-Fi connected devices in the buildings. And we're also using card key access data, which has become ubiquitous on our site since COVID. So everyone is using a card key to get into the building. And so with those two data sources together, we're inferring occupancy in the building. And then from that, we're generating an intended schedule. So that's, you can see the two items up here is the Wi-Fi trend and then the card key data. Then we can compare actual operation of the air handler. This is what we see in the middle to our target schedule or our intended schedule that we developed. And then we can flag areas of non-compliance. So are we seeing the air handler operating, well outside the schedule and well outside the warm-up period for the schedule? We're also doing some of this work at the zone. So this is a lot of detailed work. A lot of it has a few different elements. So one is just what is the intended operation of the zone? So establishing a baseline. So we're identifying the intended airflow and temperature set points along with the schedules, and we're placing them in SkySpark as equipment metadata. So this is kind of a research exercise. We're going back to the original plans for the project, understanding the original design intent, and then updating that with current conditions. It's often, I think, not generally known what the expected operation of the building is, and we're trying to establish that and bring it into our systems. Then we recognize that some zones have special equipment that may need special space conditioning requirements. So we're doing a manual process where we're communicating with the occupants through building managers, and we're identifying exceptions to those design conditions, and then we're maintaining that. And those actually come into the SkySpark system as well. So here's like a list of various exceptions. And then we can monitor and ensure that the zone operation is actually operating according to intent. And we can use, this is not the best graphic here, but we can use these heat maps that we generally use to identify periods. So this is a week-long period, and this is going across many different zones on the y-axis, and we can identify, for instance, in cooling, when we have set point mismatches happening from our ended set points. So if it's a small difference, it could be that someone has changed the temperature set point. If it's a large difference, in this case, it might be that we're operating outside of the schedule. I mentioned occupancy sensors. You've all dealt with occupancy sensors for decades now, originally installed for lighting control systems. Over the years, occupancy sensors often have digital outputs. Over the years, we've had cases where we use those and try to use them for mechanical system scheduling as well. And I think the more we've gotten into looking at occupancy sensors, we see a lot of issues and a lot of false positives in this case. So I think well, it's generally quite a challenge to stay on top and get all those occupancy sensors working. But in particular, what we see is that in lab spaces, we see many false positives. Those are associated with heat sources and motion in laboratories, triggering false positives in occupancy sensors that are either misspecified or misinstalled. So you can just get a feel for the issue here. This is in one building across many different zones. These are the 24 hours in a day. And you can see, we know no one is coming into this building before 5 a.m., but you can see all these blips of occupancy happening all through the night. And those in general are laboratory spaces, and those are heat sources or motion that's happening in the laboratory. So, this is not a great driver of as an input to the mechanical system. So we're getting a better sense of how to specify these and use occupancy sensors properly. And then the last one that I'll show you is getting into sensor calibration. So I think you all have a sense of sensor calibration in general in the abstract. You have a sensor installed in a piece of equipment. In general, we've been focusing on air handlers, and you want to compare that sensor to a known standard. And you think, well, okay, you compare it, and then if it's different, you put an offset on the sensor. But we often find that that isn't good enough in air handlers. And so we've been getting into multi-point sensor calibration, which I'll explain here. But these are the equipment that we're using to do that. So in general, we're using cloud-connected data loggers. And so we're using that cloud-connected data logger. We're installing it, in this case, in an air handler, and we're comparing that to the permanent sensors in the equipment. We're doing this over several days and logging across all modes of operation. And what we see that as the air handler moves into different modes of operation, you can get really significant stratification in the air handler, and you start understanding, are there problems with the sensor placement? Can the sensor where it's installed actually measure things properly according to your sequences? And in general, the loggers have 4 inputs. So you can use them if you have an averaging sensor element across an air handler cross-section. You can be measuring or logging across that entire sensor element. But here's a sense of how it all comes together. Again, this is all in SkySpark. So we've tried to make this an efficient process. So you have the data coming from the Hobo data logger. It's coming through the cloud, and it's integrated, and it comes into SkySpark, and then we connect it up with the sensor point in the air handler. And so now they're coming together. You can see this as a trend here, and you can see it as a correlation scatter plot. So you can see this is a case where at some measurements, you have very good agreement between the logger and the sensor. And in this case, at higher relative humidity, you have significant disagreement by like 10%. So this is a case where you can't correct this with a constant offset. It comes into SkySpark, and through SkySpark, it's suggesting a new calibration curve in this case, or a slope of the calibration curve. And then we can apply that. And of course, you can use this same environment in SkySpark to check to see if your calibration is good. So this is post-calibration data in which we're getting good correlation across all measurement there. So those are a few little detailed areas that we're exploring related to our overall ongoing commissioning effort. And I've put information here for both myself and Chris, but as I said, he will be available for questions. Thanks a lot.
Thank you, John. That's some really, really great resources, and it's awesome to see the success of your team. So hopefully we can get to these questions at the end, because I have some myself, but we're going to move on to next hear from our speaker, John Deffenbaugh, who leads the existing building commissioning program at Pennsylvania State University and has been doing that for over 14 years. He is developing a simplified EBCX process and toolset that will be used to effectively meet time and budget-driven challenges of reducing greenhouse gas emissions in buildings. So he earned his MS in architectural engineering from Penn State and has been practicing as a registered professional engineer for over 30 years. So please welcome John Deffenbaugh.
Let me share the screen properly. Hopefully you can hear me okay.
Yes.
Yeah, so I want to thank you for inviting me to participate in this conference, and thank you for the introduction. And since Jared went over the bio, I would just say for the last 14 years, been doing this at Penn State. And so over that time, come up with some ideas. So with this presentation, I just want to share what I think some of the important features of an effective program are, and what we're working on to be more effective. So let's get started. The first thing, and I just briefly want to cover why this is important. And it's important because there are opportunities with commissioning. Commissioning can, as some of the other presenters have demonstrated, you can discover and correct issues, and all in an effort to reduce energy use and greenhouse gases. And the next point was, what are the challenges that we're facing, and why do there requires to be more effective? Why do we need to move faster to reduce more energy and greenhouse gases? And so I want to spend most of the time on the fact that yes, we can do better, and discuss in more detail some of those key features to make your program more effective. The first point I want to make clear, if it isn't to everybody, is that most building systems are not, they have correctable issues. They are not, they're underperforming. They're not optimized. As some of the other ones are mentioned, whether it's a new building or old building, that's the case. I guess on the good news to that is that many of the issues are correctable. We find that they're correctable at minimal to low cost. There are not a lot of capital expenditures required. There's many causes for these problems, lots of blame to go around for all parties, owners, contractors, and designers. And some of these pictures are some examples of, good intentions that were started for energy savings, but where they overlooked a critical item. And the picture on the left is, with BAS systems, you can do a good job with scheduling. So this is a dormitory fin tube, and we were turning off the hot water when it was in the summer. But what wasn't happening was that the water was getting circulated. So the chemical treatment agents that the maintenance staff was, doing their chem treatment, the agents weren't getting circulated properly. So it really wasn't being effective at all. So we're getting big time corrosion in certain buildings. Another example of good intentions is, precise measuring of outside air so that you meet the ventilation requirements, but you don't supply excess outside energy or outside air CFM. But what we found is with the thermal dispersion type of airflow measuring stations, that they're very susceptible to dirt. And so in the outdoor air application and the return air application, we were getting errors like 5-10-fold, and it was on the bad side. It was under reporting. The control system would say you were getting 1,000 CFM, and we were actually getting 10,000, 5,000 CFM. So big energy impact there. So just quickly in summary, commissioning is a proven process. You'll get energy reductions. You'll get greenhouse gas emission reductions. You'll improve thermal comfort. And you'll tend to lower operation and maintenance costs. So what are the challenges that we're facing right now? And we're all facing or should be facing the ticking climate change clock. And we have, like most institutions, we have aggressive greenhouse gas reduction goals. But at the same time, budgets are tight. We're currently under it's modest, but a 3% budget reduction and a hiring freeze. So to meet these goals, we have to work with what we currently have. We're not going to get, it's difficult to get more resources. So the other thing is that because of our program's been going on since 1999. So because of past successes, we've reduced the energy savings potential when we go into a project, and we have an ongoing attentive, knowledgeable staff. So it makes the commissioning much more difficult than it would have been, say, 25 years ago. So what are the key features that I found it's important? And the other thing I think is interesting too is that, I guess it's human nature. Our focus was so much on the building performance, what other people did wrong or were doing wrong, and not like a self-audit on, could we make this process more efficient? And so came to realize that we probably needed what I'm calling an industrial engineering upgrade to the process to better meet those challenges and to be more cost effective. And I just categorized some of the groups that we're focusing on, and that one is, and I'll talk about these in more detail, but that is that we do a better job with prioritizing our scope. All of our efforts should be prioritized and based on payback. And then another important thing in time savings is do we have that good access to building data, and then project management software to guide and monitor the project, and then just a general category of tools. Are we utilizing, or do we have better processes and better tools to increase our efficiency? And then I thought there was a characteristic of our team approach that we have that I think helps with our effectiveness. So let me move to the next. So the guiding principle, I want the guiding principle for all our work to be that we're always working on the highest priority items. And I know some of the other presenters have mentioned the similar concepts, but so I want to be guided by, we make some projection of energy savings, make some projection of, and we use tools to do this, but of expected project cost. And then, you calculate the simple payback. So, to put it in words is we're trying to buy energy reductions at the lowest price. We're trying to be good consumers. And some of the things I want to mention about that is that fortunately there's many common issues that can be corrected with very low cost, and those typically will be through the BS control system, parameters, logic, things like that. And not all the issues are weighted equally as far as energy impact. I'm much more interested in a fault coming down on or with a 50 horsepower supply fan and an air handler than I am with a 3 horsepower hot water distribution pump. And then the discipline to stay focused, because invariably when you're commissioning, you can see low priority things that might kind of bug you, like a bad graphic or some other thing. So we document those things and try to move on if we're going to stay on target to meet our goals. So one thing that's been very helpful and I'm kind of proud of, and that is we have a commissioning website that has building information and the commissioning process information. So each building has a web page. Well, the website, each building has a page, and that page, you can see at the top, the colored, those would be links. So we have links to plans and risers and exterior building elevations, roof photos of the roof, photos of the equipment. And of course, this is all accessible for the team to improve productivity. And by the way, it's used by people outside of our group, other people in physical plant. A lot of times if a consultant's doing a project, they ask for to get access so that they can look at what information we have on a building. So as an example about how it's such a major time saver that helps the engineer jump right into, provide informed and timely responses to any questions or problem solving with commissioning. So I've kind of circled, say there's some question about a zone in the corner of a building. So, I'm literally just a couple clicks away from, I can bring up the floor plan. I can bring up the HVAC plan. I can bring up the, what air handler serves that particular zone. Bring up the VAV box schedule from the original design drawings, bring up the BAS schematics, sequence of operation. In a lot of cases, we also have the submittals, not always, but and so when you combine that information with the live BAS information, it really, you can, as I said, you're right into the problem solving mode, not and after living with on both sides of this before we got this up and running, I can't imagine going back to the old way without this website. I would look for another job. I wouldn't do it. So so another key component, I think, is the project management software. We've been using it for about 3 years. So when we started building, the building would have checklist for that, commissioning checklist, and obviously there's a lot of advantages of having checklists, but the nice thing about it too is that we have pre-made checklists for that drive the project, that drive the commissioning task. So it helps us to maintain focus and make sure we're completing the important items, the priority items. And it's very useful for tracking progress and sharing that tracking with the whole team. And then when you're going through the checklist, with this software, you can create spin-off issues that you assign to different team members. And with that issue tracking, there's a place for comments, and you can add supporting documents, like say someone says there was a problem with there's a dirty coil or a bad actuator. You could take a picture of it and attach it to that issue. So it's nice with everything all in one place. And we're getting good feedback, because sometimes when you launch new software, people are resistant to use it. But if I forget to load it up, the new building on the site, the team tells me right away, hey, get that loaded up. So we want to start using, we want to use it for the upcoming project. And so it's very user-friendly for sorting and filtering. What else did it? Well, I don't know. We'll keep going. So another feature is that you're using commissioning processes and tools, for better results, to get better results in less time. And some of the areas we're using those tools are for project selection and scope selection, and we're using it for determining project budgets. And really, the project budget is just time allocation. It's not a request for funding. And we're using it. Another area that we're focusing on is being more effective with testing. If I have some time, I'll talk about that. But I really want to concentrate on two things, and that is using better use of the data that's in the BAS system, and the other thing is we have two guides, like an energy reduction guide and a fault like troubleshooting guide. So let me show those a little bit here. So what we're doing with the energy reduction guide is it's trying to build somewhat of an expert system to evaluate common correctable issues. And I mean, if you look over the list, I know the font's kind of small, but you see some common issues like schedules and unoccupied set points and VAV set points, minimum airflow set points, DAT control, economizer, the things that you would expect to be on the list. But with this system, and again, we'll use this guide during the screening period for deciding what the scope of the project should be, what opportunities seem to be in that building, and then you use it throughout the project for analyzing the conditions, and it's so it's built up on an outline. You have like 6.0 is fan speed control, and then 6.0 will be broken down further, numerically broken down, so you can keep track of things. And trying to do a priority thing like the red, Roy G. Biv thing. The red is higher priority than yellow for someone exploring, how we're doing in these certain categories. And so it gives a description and how you would manually check that. And I didn't have one there, but there would be an FDD check for that too that we're working on. So the whole goal of these guides is really that we allow less experienced and maybe less skilled people do good work in commissioning, with less engineering input, less input on my part, that they can solve problems without my support. And now that guide's going from discovering faults, and this guide is, if you've discovered a fault, what are you going to do? And as I said, so it wants to determine the probable cause of that fault. And we're going to be using this in our, like in our FDD triage. So, say you have a fault, and we're using this in SkySpark, we have a fault that the supply fan static pressure is less than the supply fan static pressure sensor is reading less than our reset static pressure set point. So what that's going to do, the logic is going to drive that fan to full speed. And this could be occurring for some time. So naturally, that's a fault that we want to discover. But when we find that fault, what are we going to do about it? So this guide would help the resolving person or team to focus in on what the probable causes are so that they can solve that. And I guess another way of summing up these guides, like I tell my supervisor, is that I'm trying to replace myself so that, that we could hire an engineer with a couple years experience, and he could do 80–90% of what I was doing. I'm closer to retirement, so I can say things like that without I don't worry about that. So I want to be replaced. And then another thing that we're doing is something I refer to is like manual FDD, because we are starting into a pilot project with plans to scale it up. We're using SkySpark, and we're developing our own FDD system with using SkySpark as the engine. But in the meantime, and that'll take a while to get deployed. So in the meantime, I want to kind of operate as if, a manual FDD. It's not quite as quick as FDD, but it's still a big time saver. So this is an example how we can, we're using this is ALC, Automated Logic Corporation. You can do customized reports. This particular one, I know it's hard to read, but it's about VAV zones and what the airflow set points are, and what the current flows are, and damper position and things like that. And then we have ready to go, I'm on time, okay, ready to go spreadsheets that we export that data as a CSV, throw it in the spreadsheet, and the spreadsheet does analytics that in the future, or as we get it deployed, the FDD would do. And the one thing about this process, it's been very good for us to, you can't do FDD if you don't know how you would do it manually. So it's been a good exercise, even though this is kind of a bridge to, and it'll fade away as we go all FDD. So last thing I want to touch on quickly is, and some people have mentioned this, everything I talked to up to this point is kind of new developments we've done over the last so many years since I started here. But the program I inherited and we continued with had this team approach that I think has been very effective. And one of the main features to it is that the commissioning team, we're all in one group, and we have BS analysts, we have engineers, like myself, 2 engineers, and we have field technicians. And when we're working as a team and working on problems, we're getting these multiple perspectives on the same issues. So it's that kind of collaboration is good because everyone's learning. We're all getting better at things by getting those perspectives. And the other one is very important, is having common goals without conflicts of interest. I've been involved in commissioning projects where the owner's maintenance staff doesn't really appreciate me being there because I'm going to point out mistakes or at least things they weren't paying attention to on the maintenance side. And sometimes I worked in situations where there's a third-party controls consultant that the owner hires. And so invariably, I'm going to find out sequences that weren't very developed. I'm going to find errors in the BS logic. And so we're really finding, we're pointing out people's mistakes or things that they weren't doing, don't reflect on our team. So that's good. And then we have good workflow control that it's self-directed by myself and another engineer without any outside control. we're not waiting on requests for a work order to get something tested. I can call a tech up on the phone and have him totally change what he was doing and send him to another building if I need information right now. And I don't need to request or do justifications for project funding. And then lastly, we have the familiarity with working with consistent team members. So that kind of, yeah. So thank you. And I went a minute or so over, so we'll go to questions now.
John, great presentation. Yeah, hopefully we can answer, as many as we can here, but we've gotten some great questions to come in. I'll start with Julie. We have a question about how you got your environmental health team to sign up on the reduced air changes, I think specifically in the lab spaces.
Yeah, that's a really good question. And there's a couple of factors that went into that. I think the first is creating a relationship with your risk management group or environmental health and safety group, and having communication, kind of a constant communication with them about it. But on the kind of data side, we had a new building project go into the 8 and 4 air change hours. It was our biosciences building, and what was asked of a consultant was to do a CFD model comparing the 12 and 6 to the 8 and 4 to see what the actual difference would be in terms of distribution around the room, and then how the system would react in a spill event. So we had an existing building already operating at the 8 and 4, which helped us set a precedent for turning down our future buildings. And then we collected a lot of information from, I think Yale University has a really good white article on it about how quickly spill is diffused from a room based off of different air change hours. And the difference between 8 and 12 is not actually that high in terms of time to removal. And so it's not a linear correlation in terms of air changes. It's actually much worse versus like 12 and 6. Like the difference is much higher, like unproportionally higher, not just linear, for 12 and 6 versus 8 and 4. And so what we ended up doing is we ended up collecting a lot of information from other universities surrounding the dispersion in a spill event, and then also collecting a lot of information on what the different standards have. So there is no one standard that says this is what you must operate your building laboratories at. A lot of them have ranges. And so we also put together a list of all of the different best practices, standards, ASHRAE and whatnot, and said, look, these are the different air change hours that these ones recommend. And most of them recommend anywhere from 4 to 8 or 4 to 12. And these apply for, those air changes apply for wet labs, but the requirements for animal facilities are obviously a lot higher, and a whole separate discussion.
Okay, yeah, thanks. We've dealt with a lot at UC Davis too, and we have a lot of animal facilities too, so we have to work with both. Thank you. And I saw there was some messages back and forth answering each other's questions, so I think I'll skip those for now, just so we can move on. But there were some questions about Wi-Fi, which is a whole nother topic itself, but I'll kind of move on here. So question for John Deffenbaugh. The question is, I understand Penn State has a strong initial commissioning program also. How is the initial commissioning information and data used in the RCX process? And then how is the initial and retro CX team collaborate?
There isn't a lot of, well, let me just say that when there's when a new building comes online, it's generally third-party commission, new commissioning, if that was the question. And then So I'll look at the commissioner report. Sometimes, unfortunately, you see open-ended issues that weren't resolved. It's like the project team moved on, wasn't funded or whatever. So we want to know about those. The other thing is, even when, and we have good consultants doing the initial building commissioning, but we always do like what I call like a turnover commissioning. And because again, new building commissioning says, let's get the building working as designed. But in a lot of cases, working as designed is not good enough. And so they're not taking advantage of some of the control sequences and strategies that we would have wanted them to have. So that's kind of how we interface with that. I don't know if I directly answered the question, but that's some ideas about that.
Okay, thank you.
If I could add something there, this is a challenging area, but we have a new laboratory that's under construction, and for the first time, the commissioning agent in that project is doing it through SkySpark, so it's automated commissioning test scripts in SkySpark, and so we're starting that process of trying to sort of make a seamless transfer of what they're doing in SkySpark at the construction site and bringing that over into operations as seamlessly as we can. And I think that could be very valuable, but we haven't done it yet.
Thanks, John. And I see you've responded to some of the questions and from Nico in the chat. So thank you for those. We do need to move on. So I want to thank the speakers again, Julie, John, and John. I want to emphasize to the audience too how great these examples are, for your campus and just in general for energy and decarbonization projects.